All right. Next, we're going to look at section 4.6, which is change of basis. So section 4.6 is a little bit of an application section. We will be applying the concept of a basis. Right, so recall that from section 4.4 that if you're given a vector S, and we're given the fact that S is a basis for a vector space V, remember then it means every vector in capital V, call it V bar, can be written as a linear combination of the vectors in S, and the vectors in S is linearly independent. Now, we also established that when we look at a basis, every vector has a unique representation. And what I mean by that is the following. Right, so let's say there you've got your first representation, okay? And there you've got your second representation, right? The representation is unique in the sense that these values are the same. Now, we actually did the proof in the first semester. So that's the fact that the vectors in the basis are linearly independent will guarantee that these representations are the same. So what is the coordinate vector with respect to a specific basis? What is that coordinate vector again? What's the definition? Right, the coordinate vector, given a specific representation, is given by the following. It's given by this vector here, which is just basically the vector which has components that are derived from these coefficients. And remember, for each representation, as I said, for each representation of V, we only get a unique set of those coefficients, right? Because we said that a basis only uniquely represents each vector as a linear combination. So you can only find one such coordinate vector. So when you write a vector V as a linear combination between these vectors here, then those coefficients that you solve, as in C1, C2 up until Cn, that will form the coordinate vector of V with respect to the basis S. Okay, right. Okay, so given that, now what's the application of that? All right, so suppose you're given two bases. Let's call the basis S and S prime. And suppose now I've already obtained this vector here, and I want to find the coordinate vector with respect to my new basis, call it S prime. Then it turns out you can use this vector here to obtain this vector and vice versa. So this is the application that we can jump from basis to basis and find coordinate vectors with respect to different bases. If I already have a coordinate vector of one basis, then I can go and find all the coordinate vectors of other bases with respect to the vector V. All right, so perhaps it would be in order for us to just look at an example. So let's take this simple case. You've got two bases, basis B and basis B prime for a vector space, and both bases have the two respective vectors U1, U2, U1 prime, and U2 prime. Right, so I can go and take my first vector U1 prime in the basis B prime, and I can go and write it as a linear combination of the vectors in B. And remember, B is a basis, so I can by the property of a basis spans the whole vector space V. So that you can certainly do that. Right, and then you can do the same for the second vector. You can write u2 prime as a linear combination between the vectors u1 and u2. So the coordinate vectors with respect to the basis b become, right, so there's u1 u prime with respect to the basis b, that's my coordinate vector. Right, and my second vector u2 prime with respect to the basis b becomes that vector there. Right, and now let's take a vector v. And we write that vector v as a linear combination between the vectors in b prime. There's that linear combination. So what is the coordinate vector of v with respect to the basis b prime? What is that vector? So the coordinate vector v with respect to the basis b prime is the vector k1 and k1, k2. Now the question becomes, what is the coordinate vector of v with respect to the basis b? How do we get that? Using this coordinate vector. So now the question essentially is, what do I want? What is this? How can I find that? How can I find this? That is the question. Alright, so our aim is now to determine that. Right, so what can we see from here is we have an expression for that vector and we have an expression for that vector. So we're going to substitute it in there and we're going to substitute it in there. Okay, do that. So we take v and we do that substitution there. Okay. And, right, we take the second one there, plug it in there. Okay. Okay, and then simplifying, we obtain. Right, there we go. We found our simplification. And note now that we've expressed v as a linear combination between u1 and u2. And remember, the representation of a vector in terms of a basis is always unique. So therefore, these are the unique coefficients, the only coefficients that you get. So therefore, we can determine the vector v with respect to the basis b as follows. Right, so the vector, the coordinate vector with respect to the basis b becomes that vector there. Okay, so again, it's just these components that or these coefficients. All right. So basically, what can we write this column vector as? All right, the column vector I'm referring to is this one here. What can I write that as? Right, we can write that as we can write it as that product between a 2 by 2 matrix and that column vector k1 and k2. Right, and what is that equal to? Remember, what is this k1, k2 vector? What is that equal to? Right, it's equal to the following. Right, there we go. K1, K2 can be replaced by that quantity or vector. Right, so what have we done here? We've established this vector as a matrix multiplied by the coordinate vector of v with respect to the other basis. Right, now you can do the same. You can obtain the coordinate vector v with respect to the basis b prime in terms of this that vector by just doing the reverse and multiplying with the inverse of this matrix on both sides. Okay, so having one basis representation, you can find another basis representation. Now you can follow this same argument for bases that contain more than two vectors. Okay, and then the argument is exactly the same. Now we will define this matrix here. Later on, we define that as the change of basis matrix. That just brings us to the following example. Just a look at the case of a different vector space P2. Here you've got two bases for P2. And what's P2 again? It's all polynomials of degree at most 2. Now if you take the vector Px, which is this polynomial here, then it's easy to see that the coordinate vector of Px with respect to the basis B is just now what's the basis B? We know what that is, 1x x squared, and therefore the coordinate vector is just 2 minus 1, 3, and again for B prime it's a different story. There we have to do a little bit more calculation. Alright, so there we take the vector Px, 2 minus x plus 3x squared, and we write it as a possible linear combination between the vectors 1, 1 plus x, minus 1 minus x squared. Alright, so gathering all the terms on the left, you get the following polynomial. Right, and from there, it follows that, okay, again, remember that this polynomial must be 0 for all values of x, and therefore that is going to force that value to be 0, that value to be 0, and that value to be 0. Why is that again? Because if this value is not 0, then you're going to have a polynomial on the left hand side that has degree 2 equals to 0 for all values of x, and that is going to be impossible because a polynomial of degree 2 can have at most 2 roots, but in this case the polynomial is going to have infinitely many roots, which is impossible. So therefore that has to be 0. If this is not 0 again, you've got a polynomial on the left that's 0 for all values of x, and the polynomial on the left is going to have degree 1, and a polynomial of degree 1 can only have at most one root, but if that's not 0, you're going to have infinitely many roots. Okay, so that's 0, and that also needs to be 0 for the same reason. So therefore we get, right, so therefore we can solve k1 as 0. Okay, so my coordinate vector are px with respect to the basis b prime, right, is equal to the vector 0, minus 1, minus 3. Okay. Right, so there we've got our coordinate vector. Right, so let's take all that and go and write it mathematically. So if you've got two bases, B and B prime, for a vector space V, right, they're both bases for the vector space V. And let's take an n by n matrix whose columns are these coordinate vectors, u1 up until un with respect to b prime. The coordinate vectors of the basis b with respect to the vectors with respect to the basis b prime. So what you do is you take u1, you write it as a linear combination of all the vectors in b prime, and you read off those coefficients, and you form the first coordinate vector, and you do that for all your vectors in b and b. Now the matrix formed in that way is the matrix that that's called P subscript B to B prime. Okay, and that's the transition or the change of basis matrix. And the change of basis, remember, we want to move from the basis B to the basis B prime. So whenever you move from one basis to the other, the one that you're moving to is the one that you use to represent the vectors of the old basis. Right. So writing that down, that gives us the change of basis matrix. Right. So remember this order. You have to be very careful with that. That's where students tend to make mistakes. So you need to be very sure of the matrix that you're working with. So going from B to B prime, B is your old basis, B prime is your new basis. Okay. And the basis that you write the last is going to always be that one there. Okay, so don't forget that. Right, so writing the now what I want to look at the coordinate vector of V with respect to the basis B prime, and all I do is I work out the coordinate vector of V with respect to the basis B, and I multiply that on the left with the change of basis or transition matrix, and that will give me the required vector. So remember what I said, B is the old basis and B prime is the new basis. You always write the old basis first and the arrow points to the new basis. So the columns of the transition matrix P are the coordinate vectors of the old basis B relative to the new basis B prime. Right, so let's look at the following examples. So there we're given a basis. It's a simple one. It's an R2, and we're given the new basis, right? And you can verify that they are both bases for R2. So here's a straightforward question. We want to find the change of basis matrix from B to B prime. So B is my old basis and B prime is my new basis. Right, so there we've got our first question that we need to solve. So let's look at the solution. Right, so remember now we want to find that basis. So what's the old basis? The old basis is B and the new basis is B prime. So to find we need to now take the vectors in B and write them as linear combinations of the vectors in B prime. So we take the first vector in B, which is 1, 0, and we go and find the coordinate vectors of 1, 0 in terms of we find the coordinate vector. So we're going to take 1, 0 and write it as a linear combination of the vectors in B prime. Alright, so setting up our linear equation, we can solve these coefficients as -2 and 1. Right, so there we've got -2 and 1. Right, so next we take the vector 1, 1 and we go and write it as a linear combination between the vectors in B prime. And there we have the linear combination. Right, so having written down that linear combination, we can then read off our values for the coordinate vector, which is -1 and 1. And there we have our column vector -1, 1. The change of basis matrix is now the matrix that you find by making your columns these coordinate vectors. Okay, so there's my coordinate vectors. And that gives us the change of basis matrix. So that answers the first question. The second question there, they ask us just to verify that the coordinate vector v with respect to the basis b prime is in fact change of basis matrix multiplied by the coordinate vector of v with respect to b. Now to do that is not difficult. Let's determine the coordinate vector v with respect to the basis b. Okay, so let's first determine the coordinate vector v with respect to b. Okay. Right, so there you set up your linear equation, and from there you can find a system of linear equations, and it's two equations, right? There we've got our first equation, and there I've got my second equation, and that's linear, so let's solve it quickly. So you can solve k1 as -8 and k2 as 2. Right, so there we've got our -8, 2, and then plugging in everything, this we solved, that we solved, so that's that 2 by 2, multiplied by that 2 by 1, and we get 14 minus 6. To verify that, that is in fact the case, let's go and work this out separately. And working that out separately, right, we do that by writing the vector -6, 2 as a linear combination between the vectors in b prime. Okay, and that's easy to do. So that's the first one in b prime, that's the second one in b prime, and you can easily verify this linear combination, that 14 times 0, 1 minus 6 times 1, 2 is in fact -6, 2, which is the vector v. Right, so this is a little handy formula that you can use to play around with coordinate vectors between different bases. Now again, we can extend this to include multiple vectors, not only just two vectors. Right, just some important remarks. The order is important, as I stated previously, so keep the order of both basis sets in the representation of the transition matrix. So start with your old basis, and the arrow always points to the new basis. Okay, and when using the transition matrix, the old vector multiplied must be a coordinate vector, and the product gives the new coordinate vector. Okay, and then to find the vector itself, write the vector as a linear combination of the basis vectors using the coordinate vector. Okay, so the process is simple, but the orders are important, and that's normally where the mix-ups occur, so be careful with that. That brings us to our first theorem, which basically just says the following. It says something about the change of basis matrix. So given two basis for a vector space V, the change of basis matrix from B to B prime is always invertible. Okay, and it just happens that the change of basis matrix from B to B prime, the inverse of that matrix, gives us the change of basis matrix from B prime to B. So to go from B to B prime, we just take, well, to go from B prime to B, we just take the matrix from B to B prime and take its inverse. Right, and we can sort of see that P B to B prime is invertible. I mean, if you look at, recall the equivalence theorem, if you have that matrix set up there, and B is an n by 1 matrix, right, then we said that A is invertible if and only if this system here has a solution or is consistent for every matrix B. Now, if you go to your actual formula, if you go to your formula here, this is of a similar setup, right? Again, this is an n by 1, just like that vector there. That's n by 1, and this one is also n by 1, right? N by 1. So remember, we established that you have a unique correspondence. So if you have this coordinate vector there, that any n by 1 column, that's just a representation of the coordinate vector of some vector in your vector space. And the same for this vector as well. We said that we can uniquely solve for this vector in this particular form. So again, that is going to force this matrix to be invertible. And taking the inverse of this matrix on both sides, we can then just switch the b's and the b prime. We can switch that around, and by the same argument, you can follow a symmetric argument, and then solve for v. Coordinate vector v with respect to the basis b in terms of the coordinate vector v with respect to the basis b prime, and the inverse of this matrix will in fact be this matrix. And again, you can follow a similar argument to what we did in the beginning of the lesson, and just reverse the b's and the b prime and find a similar, and see why that is in fact the case. Okay, so let's look at this example. We go to this space M22, and we select two bases, b and b prime. And remember, M22 is the vector space of all 2 by 2 matrices, and matrix addition and scalar multiplication are my two operations. So here they ask, find the change of basis matrices. The first one we need to find is the matrix change of basis matrix from B to B prime. Right, so now we follow our notation. Okay, so we start with our old basis, and we label our old basis in this case is B. And what we do there is we label our vectors u1, u2, u3, and u4. And we want to find the transition matrix from B to B prime. So what in notation, what is it that we want? That is the matrix that we want. Okay, so it's you take each vector in B and write it as a linear combination of the vectors in B prime, and then you just read off the coefficients and form your columns in that way. Okay, so let's write that down. Okay, so we want our change of basis matrix. Okay, so we take our first vector. There's our first vector, and we go and write it as a linear combination of the vectors in B prime. Okay, and that is my linear combination. So therefore my first column of my matrix becomes, right, that matrix there. There's my my first column vector. And again, how do I find that? I read off those values there, 1, 0, 1, 1. Then we take our second vector, which is 0, 1, 1, 1, the matrix. And there we write it again as a linear combination between all the vectors in B prime. And so my second column becomes, there's my second column vector. Okay, and how did I get that? Reading off the values. Like that. Right, so placing my two vectors together there, we can find the coordinate vectors of the other two remaining vectors in the basis B. Right, so there we've got our two remaining vectors in my basis, and I've written them as linear combinations of vectors in the basis B prime. Right, so reading off the values we get. Right, so we get the coordinate vector with respect to the basis B. How did we get that? Again, you read the values. Okay, so doing the next one, we get, right, reading off the values we get for coordinate vector with respect to the basis B prime, we get that column vector. Right, now throwing all of that together, we get, right, there we go. Right, so there's my third column. And my last column becomes that there. Right, so my change of basis matrix then becomes that matrix there. Right. Alright, so what is it that we want now is we want to find the change of basis matrix that runs from B prime to B. And recall that we can do this by playing around with inverses. So from the previous theorem, the change of basis matrix from B prime to B is just the inverse of the change of matrix from B to B prime. So now that we have our change of basis matrix from B to B prime, we can easily determine the change of basis matrix from B prime to B, which is this matrix here, by simply taking the inverse of that matrix. Right, so there we have our information, and if we look at our change of basis matrix that we derived, we get that one there, and here you see that is my change of basis matrix, and there we want to find the inverse using Gaussian elimination. So we write down the identity matrix on the right hand side, and we use Gaussian elimination, and we rewrite this matrix here using row operations to find the identity matrix on the left hand side, and whatever is on the right hand side is my inverse. So therefore the change of basis matrix from B to B prime is simply the inverse of the change of basis matrix from B to B prime, and it is that matrix there. Okay, so take note that we can jump from one basis to the other from the transition matrices by taking the inverses. Okay, let's, for interest's sake, let's go and find the coordinate vector of V with respect to the basis B. And V is given as the vector 1, 2, 3, 4. What we want to do is we want to find, we have that formula for the coordinate vector of V with respect to B, and it's given as that. Right, so go and write that vector as a linear combination of the vectors in B prime. And essentially what I'm doing now is I'm determining that that vector, that column vector. Just recall what B prime was. It's 1 is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 1, 0, 0. Right, so reading off my coordinate points, we get all right, so therefore we have got the following. Recall that my change of basis matrix, that one there, is that whole vector. Okay, so the change of basis matrix we're talking about here is that one there. Right, so plugging all of that in and working it out, we get this expression. Right, so we took that and we multiplied it with that vector. Okay, so that's the application. So the coordinate vector of the matrix V with respect to the basis B is this vector. Right, now it happens that there's another type of method that we can use to jump from one transition matrix to the other, and it's by the Gauss-Jordan method. So again, given two bases of a vector space V, what we do is we distinguish between two matrices, B and B prime. Now, B is formed by taking all the vectors in B and forming the columns of this matrix as follows. You take E, which is the standard basis for the vector space V, and you go and write down the coordinate vectors of each vector in B. You go and write with respect to the basis E down, and you form these column vectors using the standard basis E. Okay, and you do the same for the matrix B prime. You take every vector in B prime, go and write its coordinate vector with respect to the basis E down, and you form the columns of the matrix B prime in that way. Now, what you do is you place the matrices B prime next to one another in another matrix, and you separate them. And then what you do is you reduce the matrix B prime to the identity matrix using row operations on this whole augmented matrix. So it works very much in the same way as we determined inverses. You took a matrix, you placed it next to the identity matrix, and you used that whole matrix, row operations, to get the inverse. And whatever you left with at the very end on the right-hand side, that will be the transition matrix from B to B prime. Okay, so take note of the order here. You see, we go from B to B prime there, and we place B there, and we place B prime there. All right, so if you were to turn it around, B to B prime, okay, then you would reduce that to the identity matrix. Whatever you get on the left, that will be the transition matrix from B prime to B. Okay, right, so it's very important order in this case. So going back to our theorem, you start with a new basis. Your old basis is on the right hand side. Okay, so my new basis is B prime, and my old basis is B. So you place the old basis second, and you place the new basis first, and you apply the Gauss-Jordan elimination method to reduce the new basis to the identity matrix, and whatever you get on the right will be the transition from old to new. Alright, so let's look at an example. So we look at P2, we look at the basis B and the basis B prime there, we are asked to find the change of basis matrix P from B to B prime. So B is my old basis, B prime is my new basis, using the Gauss-Jordan method. Okay, so what we need to establish first is what is the standard basis for P2? So we need to find the standard basis. We know the standard basis for P2 is 1x squared. Right, so what is the matrix B again? The matrix B is this matrix. It's the matrix with the columns. You take the vectors of B and you write them as linear combinations of the standard basis. Now, what is the standard basis in this case? The standard basis is E, right? So what's my first column going to be of B? My first column of B is going to be, right, so we take B, the first vector of B, there it is. Right, we write that vector as a linear combination of the vectors in the standard basis. Okay, there we go. We write our three vectors down. Right, and that is equal to 1 plus x plus 0x. Okay, so our first column of my matrix B becomes, right, so we take our first vector there. Okay, we make it a column vector. Alright, and we form our first column vector there. Vector. Okay. And finding the coefficients there, we get 1, minus 1, 0. Okay, so there's my second column. Right, and then we take our final vector in B, which is x squared. We take the elements of our standard basis. Okay. Reading off the coefficients, we get 0, 0, 1. Right, there we go. And that is my matrix B. Right, next for the second basis, B prime, that's the matrix that we want. Right, so we go and write 1 as a linear combination of the standard basis. 1 plus x is a linear combination of the standard basis, and minus 1 minus x is x squared is a linear combination of the standard basis. Alright, and that can be done in a similar way as the previous case. So there we have our column, or the columns of my matrix that I put together, and it gives me the matrix B prime. Alright, and now we can go and continue from there. Okay, so we want to set up that augmented matrix B prime B, and then what I eventually want to do is I want to reduce it to that form there. Okay, so we need to do that now. Okay, there we've got our matrix B prime. And there we've got our matrix B. Alright, And now putting all of that together and doing row reductions, we can get the following. Right, then we take negative the last row and add it to the first row, and then multiply the last row with -1 and get. Right, then we take negative the second row and add it to the first row, and we get our next step. Okay, moving on. We get to our last step, and therefore our required matrix becomes the matrix on the right hand side. Okay, so clearly you can now read off the change of basis matrix from B to B prime, which is that one there. Okay, so by our Gaussian method, the change of basis matrix becomes okay, so that's our change of basis matrix from B to B prime.